Dear friends, as you could understand, I have always been interested in the physical laws that govern the way of the world works, the force vectors of our gestures that explain our choices of craftsmen, as well as the pathology results that give consistency to our surgical intuitions. This is why in 1998 I spent for 6 months with a specialist in fluid dynamics to understand why every time I tested a machine equipped with a venturi pump, I did not have the same quality of vitrectomy as with a machine equipped with an aspiration flow control. I understood why, and therefore built a film that I presented in the 2001 at the first IVIRES Congress in Biarritz. Here is an excerpt dedicated to fluid control. Please note, in 2001, there were only 20 gauge systems available, and the figures you will get with 23, 25 or 27G systems will be different since the flow rate vary according to the internal diameter of the tubing. But the principles and consequences remain the same. So let's take a look at these first fundamentals of fluid dynamics.
We do not pick a vitrectomy machine like we do a vacuum cleaner, considering its power, color, and brand name. Everything we ask the vitrectomy machine to do is so vital to the final result that we can't possibly be satisfied by a machine that only nearly achieves our goal. We ask for a precise control of the quantity of the vitreous that enters the end piece in order to avoid aspirating or tearing the floating retina to which it is attached. Thus we ask for a precise aspirating flow control. We ask for a quick and efficient cut without pulling out or moving the retina. And finally we ask for a stable intraocular pressure during the entire procedure, and so we want the machine to adapt its infusion flow to the aspiration flow. The problems are that we are working in a complex environment with varying viscosities, and that the machine is not intelligent. It can only respond to our commands while also obeying the laws of physics, in this case the laws of fluid dynamics. The laws of physics remind us that the flow of fluid in a tube is equal to the displacement speed of this fluid by the internal surface of the tube. The speed of the fluid is determined by the difference in pressures, the only possible motor for carrying out a fluid displacement. Fluid speed is slowed down by the forces of friction, which depend on the internal roughness of the tubing walls, and most of all on the viscosity of the fluid. The internal surface of the tubing depends on the tubing's diameter, and can also be influenced by the compliant forces under the effect of depression. To the best of my knowledge, only one experimental study has seen how the laws of fluid dynamics directly relate and apply to current vitrectomy procedures. The 2001 study by Jean-Christophe Bidet and Bernard Collin. They have allowed me to incorporate the results of their findings in this presentation. Let's now see the infusion. Things are fairly simple here. Friction hardly occurs at all since BSS is not viscous, and there are no compliant forces since there is no depression. The only elements in play are the gradient of pressure and the internal diameter of the tubing. The gradient of pressure is linked to the pressure of infusion, which in turn depends on the height difference between the drop counter of the bottle and the eye. When there is no escape or aspiration, an immediate equalization occurs between the infusion pressure and the intraocular pressure. These two pressures vary according to the height of the bottle. If a leakage or aspiration were to occur, the intraocular pressure would decrease, causing the gradient of pressure to be responsible for the infusion. This infusion will be proportional to the diameter of the tube. Bidet and Collin confirm these facts. In the absence of aspiration, an infusion of 70 centimeters carries a pressure of 51.7 millimeters of mercury in the eye and throughout the aspiration tubing. This infusion pressure is responsible for a flow of 36 cc's per minute in the air. The frictions in the eye diminish this flow to 23 cc's per minute. The frictions at the level of the handpiece, as well as the aspiration tubing, further reduce the natural flow of BSS at the start of the pump to 8 cc's per minute. Two surgical consequences become evident. First of all, for a bottle at 70 centimeters, when you connect the infusion tubing tip and open the infusion, the intraocular pressure is going to be quite large. One certainly needs a good infusion pressure in order to obtain an infusion flow that is sufficient enough to compensate for the aspiration flow. However, if one raises the handpiece without having clamped the infusion, the intraocular pressure that had established itself will cause a vitreous incarceration, a serious complication. Thus it proves absolutely necessary to control the infusion with the pedal, as in phaco. Secondly, seeing that a gradient of pressure of 51.7 millimeters of mercury between the bottle and the pump already carries a natural flow of 8 cc's per minute, if one were using a Venturi pump, it would only be possible to add an additional depression, resulting in a higher gradient of pressure and thus a higher aspiration flow, greater than 8 cc's per minute. The minimum flow when using BSS for a depression of only 5 millimeters of mercury will be 8.4 cc's per minute. Only a debimetric pump, like the peristaltic pump, thanks to the slow rotation of the rollers, will be able to slow down the natural flow of BSS. This will also allow one to control the water flow from 0 to 8 cc's per minute without difficulty. Let's see now the aspiration flow. During a vitrectomy, it is necessary not only to remove the central vitreous, but also the posterior haloid, the anterior haloid, and the peripheral vitreous, all of which necessitate different aspiration flows. Here is an example. In this case, the retina is far away from the center of the eye. Therefore, the central vitrectomy will not pose great risk. One would want to be quick and efficient, and then would desire to use an elevated flow. Then, since we want to remove the anterior haloid without risking the aspiration of the posterior capsule, we drop the cutting frequency and the aspiration flow, This is a phakic eye, so a manual indentation is called for. With a vitreous of average periphery, I usually work between 6 and 8 cc's per minute, and then, when I want to remove the last peripheral remainders, I lower the level to between 2 and 4 cc's per minute. One realizes that it is necessary to have the aspiration flow varied according to the particular conditions. But as we have already seen, the aspiration flow will depend upon a number of parameters that must then be precisely controlled during the procedure if we hope to achieve a successful vitrectomy. This is what we are going to see here step by step. First of all, we have the gradient of pressure. The pump generates the gradient of pressure. If the pump is not turning, the same pressure is throughout, and since there is no gradient of pressure, there is also no aspiration flow. The pump functions by creating a depression lower than the intraocular pressure. Thus, the pump is able to create a gradient of pressure as well as the aspiration flow. For a liquid of a given viscosity within a given type of tubing, for a given gradient of pressure, we will always have the same flow, no matter which pump is used. It is true that some manufacturers sing the praises of their pump system, obtaining the best flow, as if the universal laws of physics did not apply to ophthalmology. But this is quite untrue. For a given liquid in a given tubing, a certain gradient of pressure always induces the same flow. The problem is that during a vitrectomy one is not working with a liquid of a given viscosity. This is easily visualized by thinking of honey in water. For a given gradient of pressure, the flow will not be the same in water and in honey. And it is here that we return to the question of which type of pump to use. A pump with vacuum control, like the Venturi pump, only allows the operator to control the depression, and therefore the gradient of pressure. One is unable to control the variations caused by the fluid's viscosity. For the same gradient of pressure, then, different flow amounts will result according to the viscosity of the fluid at any given moment. With a debimetric pump, as with the peristaltic one, the column of aspirated fluid, which fills the space that was created by the rollers, is going to be the same no matter what the viscosity of the fluid is. The flow caused by the rotation of the rollers will thus be constant, but it will bring about varying depressions at the pump level according to the aspirated fluid's viscosity. Bidet and Collin have confirmed these theories. With a Venturi pump at 1 Hz, or 60 cuts a minute, one has 15 times the amount of flow in BSS than in egg white for a depression of minus 50 millimeters of mercury, 7 times for minus 150, and 6 times for minus 300. These enormous differences are equally found at 5 Hz, 300 cuts a minute, 10 Hz, 600 cuts a minute, and 20 Hz, 1,200 cuts per minute. With a peristaltic pump operating at 60 cuts per minute, the flow in BSS and the egg white are practically the same, within 10% until 15 cc's per minute. For higher flows, the required depressions in the egg white exceed the capacity of the machine. The same findings occur at 300, 600, or 1,200 cuts per minute. Let's now consider the practical consequences in the context of a central vitrectomy. If a Venturi pump is used and if the operator chooses a maximum depression of minus 50 millimeters of mercury, the aspiration flow will decrease from 13 cc's per minute to 0.85 cc's per minute. It would be necessary to spend about half an hour performing the procedure. If the operator is impatient, like me, however, he or she may use a higher maximum amount of depression, only stepping lightly on the foot pedal at the start and using more force when the flow is too little. Here we have a decreasing flow, so the operator puts his foot down. The problem then is when returning to BSS, the magnitude of the depression will generate an aspiration flow twice as great as the infusion flow. This is easy to understand when drinking lemonade with honey. In lemonade, the depression created by your mouth gives off a satisfying flow. If you descend into the honey, you would have to create a higher depression in order to get a very small flow. With this large depression, if you return to the lemonade, you would suffocate due to the flow being so great. Here is a simulated operation. At first, there are few friction forces and thus a good flow. But later, while the vitreous is coming through the tubing, the operator puts more pressure on the foot pedal. When water will flow back in the tubing, a catastrophe will occur. With the peristaltic pump, the operator selects not the maximum depression, but the maximum flow. Here it is around 12 cc's per minute. He or she will use depressions around -500 millimeters of mercury, which would be incredibly dangerous with a Venturi pump. These depressions will show up on the machine's screen, but the operator doesn't have to consider them, for he or she controls the flow with the foot pedal. In this way, the operator performs a more precise, but also a quicker central vitrectomy, using very high depression levels without risk for the patient. This French culinary expert will easily prove this to you. Here we have some vitrectomy aspirating tubing. It is going to be cut and placed in a glass of rosé wine of very weak viscosity. In order to simulate the action of a peristaltic pump, he will use his wife's preferred instrument when he comes back late at night, the rolling pin. For a certain number of turns of the rolling pin, he is going to pump a certain amount of wine. If he replaces this light wine with a heavier liquid, like maple syrup, and tries again, for the same number of turns of the rolling pin, he will actually pump the same quantity of maple syrup as the wine. Unbelievable but true. For the peripheral vitrectomy, it is not so much a question of going quickly, but of being precise. Using a Venturi pump in an infusion at 70 centimeters, one is not able to aspirate in BSS at less than 8 cc's per minute. Yet at the end of the central vitrectomy, the tubing is often filled with BSS. That was the case here, where I had a first alert that made me lift my foot from the pedal. But in spite of that warning, cutting at 700 cuts per minute, in less than a third of a second, the minimum flow with this Venturi pump created a disastrous problem. Seeing this again in slow motion shows us that a flow of 8 cc's per minute is sufficient to cause a tear within the space of 3 cuts. With a peristaltic pump, it is possible to aspirate at least 8 cc's per minute in water by lifting up from the pedal. One can then perform this peripheral vitrectomy with more precision. Six or 8 cc's per minute is correct most of the time for a flattened retina. In contrast, when the ciliary retina is detached, these levels may already be too much. Here is an example where I created a iatrogenic tear working at 8 cc's per minute, and only realized what I had done at the second passage. In these cases, it seems better to change the program, as we do while putting a car in first gear, opting for a low aspirating flow program with a maximum aspiration flow of 6 cc's per minute. The operator will then have the entire pedal range to go from 0 to 6 cc's per minute in trying to execute a precise and complete peripheral vitrectomy. In this case, things are easy, so we work at 6 cc's per minute. But here, in this perilous example, one is forced to drop down to 2 cc's per minute. This is of course not possible with a Venturi pump, except to place the bottle 10 centimeters above the eye, work at minus 10 millimeters of mercury, and thus spend close to 2.5 hours performing the procedure. In considering all the above, the choice between the Venturi or peristaltic pump immediately becomes a question of security and quickness, for which the peristaltic pump is the answer.
You see, it's not hard to understand. And yet, each of you knows that you have to control the speed of your car, and that the speed depends on the number of revolutions per minute of the engine and the gear in. For 3,000 runs per minute, the car will not go at the same speed if you are in first or fifth gear. And it would never occur to anyone to drive just checking the RPM counter without being able to control the gear engaged, because an accident would be inevitable. However, some of you accept very well to control only the vacuum without being able to take into account the viscosity of the fluid and therefore the friction forces, which, for the same depression, will lead to a variation of flow from 1 to 5 in the same way that when you change from first to fifth gear in a car, you will obtain a variation of speed from 1 to 5. Why this paradox? I think because speech is polluted. To sell their system, manufacturers do not hesitate to find arguments that have no physical basis, such as we will control the flow by controlling the cutting speed, which is completely absurd. Well, we will talk about this later. These arguments are repeated in congresses by medical consultants and gradually become part of an acceptable or even accepted discourse, which, depending on the power of the industry in question, will even be taken up by physicians who have never thought about it. I have tried to fight this state of affairs by presenting films and lectures, and I must admit that most of the time this has been a failure. I have never felt the audience's total support. There are several reasons for this. First, because few people are interested in physical laws. After 3 minutes, I felt that they were no longer listening to me when they were not sleeping openly. And yet, what NASCAR or Formula One driver might not be interested in how his car engine works? Also because you make efforts to master your machine, to anticipate accidents, and if you haven't tried other machines, you cannot know what you are missing. A young operator, conditioned by the habits he picks up at the hospital during his fellowship, will find it harder to admit that there are other more efficient systems, since his boss, his mentor, has chosen this machine. He will feel attacked when he hears that the machine with which he works, whether it it was chosen by the bursar of the establishment or by himself, causes 3 times more lost eyes than other machine, even if this comes from an indisputable statistic. The third reason is that many thought that I had financial interests in promoting this or that specific machine. I never patented anything in vitrectomy, alas, because I would be richer today. I do not have a contract with any industry. I have always refused any consultant status because I am too attached to my freedom of speech. And if I have given many industries the specification of the ideal machine, it is without receiving any financial compensation. I have only received active animosity from certain American industries. The problem, let's face it, is that the market is dominated by Alcon and Bausch & Lomb, and that most other industries, not wanting to disturb part of their customers accustomed to American systems, did not want to follow these specifications. And so, unless these American giants agree to admit that they were wrong, it is you, the users, who will be able to continue the pressure on these manufacturers, hoping that altogether you will be more convincing than I was. In the following chapters, I will explain to you in all impartiality which functions you must be able to control with the ideal vitrectomy machine in order to perform a safe and effective vitrectomy as complete as possible. And then we will see how to perform this vitrectomy and what parameters to use. See you later.